If you work in a private data center or you're a developer or DB admin, you should train yourself and get ready to move from traditional data centers and DevOps environments and gradually migrate to clouds. Even if you're not ready to completely shift to the cloud, you're better prepared to use partially some valuable services on the cloud. My name is Reza, and I will try to briefly showcase cloud services in this Tech 10 tutorial series. Buckle up and join me.
Ladies and gentlemen, welcome on board. Our first episode time will be 30 minutes. We will be flying just right above the clouds and our destination is just to touch the cloud surface. At this time, make sure that your seat back are in full upright position and your computer speaker is on. Smoking is allowed for the duration of the flight. Thank you for choosing Tech 10 Tutorials series.
This tutorial comes in 3 parts. First, I'm going to illustrate what a sample 3-tier application looks like and how its components and microservices are defined and layered, and how they interact in on-premises environments. Next, I'm going to show you how we can duplicate the same model on Amazon Cloud and how we can leverage different Amazon Cloud services to build and form our application. And finally, we will take a look at 2 other major cloud providers and translate every Amazon Cloud services into their Google and Microsoft's cloud equivalents. Okay, for better understanding of the requirements and the logic of the app, I'm going to mock up a mini version of social network app, which is LinkedIn in this case. We are supposed to build, manage, and maintain all hardware and software components in our private data center, which we usually call it on-premises environment. Okay, let's talk about our first design in our private data center. A typical web application usually needs 3 distinct elements: an HTTP server, an application server, and a back-end database server. As you probably know, there are some full-stack solutions out in the market that you can have all the 3 components in one place and run them on only one server, just like the LAMP or LAMP packages. LAMP stands for Linux, Apache, MySQL, and PHP, and LAMP is for Linux, Nginx, MySQL, and PHP. But for the sake of scalability and the security, we go for, let's say, a multi-tier design and create 3 networks for 3 different workloads. 1 public subnet for HTTP server and 2 private subnets, one for our app servers, or better says, our logic layer, and one another for our database servers. Like I just said, we need a fast and a scalable web server solution, which is usually referred to as front-end or presentation layer. It could be either an Apache, HTTP server, or Nginx. Nginx could be a better choice because of its superior performance. It also can do load balancing stuff for HTTP and HTTPS traffic, and it has the ability to act as a load balancer, HTTP load balancer. So we will run Nginx as HTTP reverse proxy and load balancer at the same time, and assign a public IP address to it, and then it will redirect incoming traffic to our logic tier servers, which would be in the private part of our network. Finally, we install some sort of relational database such as MySQL or MariaDB, as well as non-relational database like MongoDB for non-tabular or key values data, such as our user configuration data or their friendship network data. Now, as our application community grows, we gain more traction. So, we need more availability and more capacity in order to process incoming requests. That's why we start to scale out our web service by adding more and more servers to the presentation tier. Doing so, we can make sure that we have enough resources to serve the growing clients and reinforce our service availability, which can tolerate any kind of node failure. But the question is, how can we do that? Or how can we predict the traffic bursts and scale up the resources accordingly? There should be enough redundant resources, and that means an upfront buying of additional physical resources, physical servers, and early provisioning all of them. And even if you manage to scale your network right in time, what would you do with those idle resources when the demand goes down? You will be left out with a bunch of unused idle resources. What a waste, right? Okay, now it's time to put a load balancer to impersonate our multiple web servers with a unified IP address that can intercept all the incoming traffic and effectively balance those traffic among processing servers. Fortunately, Nginx can simply do this. Then we need a DNS name server to enable our users to reach our service by using a name instead of an IP address. To further accelerate the data query time, we have the option to insert a database cache service right between our data layer and application server. This can be done by using Redis cache or Memcache cluster, which both are in-memory data stores and provide sub-milliseconds latency data access. Now let's take a look at some extra services we need for our social network app project. One of the main features of all social network apps are media sharing, which could be audio, image, and videos. Videos in particular are relatively giant unstructured data in nature. So we need to store them on a big expandable storage, which could be a SAN or NAS file storage. But before file being published on the storage, we need to screen them to flag copyrighted media or inappropriate contents like those having nudity, guns, or violence in them. This can be done by a server that is trained with a complex machine learning model to identify and classify inappropriate objects or actions in a video. This will happen at the first stage, and then those flagged medias will be forwarded to an auditory team to be reviewed and be either accepted or rejected. And don't forget that big chunk of LinkedIn traffic is coming from mobile users, and thus we need to provide a proper media format which is optimized for mobile viewing. So we need a transcoder engine and a separate storage to store converted media for mobile app users, and then generate different URLs for different users. So when a user logs in from his app or from his web browser, he will be directed to different storage URLs to get the appropriate media format. To speed up the media loading time and smoother playback of video files, we will acquire some third-party cache or CDN services such as Cloudflare or Fastly to fetch the video contents as close as possible to our users in different geographical regions. So large media such as videos could be delivered to users with no lag. Another important feature of all social and media network app is the ability to dynamically personalize each user experience based on users' activities on the website or on the app. like tracking their movements on the pages, or their click pattern, or how long they spend watching a specific video, for example. This can be done by a clickstream engine like Apache Kafka, which is basically a pub/sub queuing service. If you ask me what exactly Apache Kafka is, I could say it's a streaming data store that decouples the application producing streaming data on its data store from applications consuming those data from its data store. You know, many organizations use Apache Kafka as their data source for the kind of applications that continuously want to analyze and react to those streaming data, just like what we have here. In LinkedIn, we also wanted to detect and collect every click that users have made on their app or web page, and wanted to react to them by customizing the viewing experience in real time. Now let's suppose we capture the user's activities, like their clicks, okay? From this point, we will have another destination, or let's say a consumer, for captured data. In one way, we can feed them back to our data tier in real time to be used by the application layer to influence the user experience, for example. And in reverse, we can import data from our data layer and pass them to our data warehouse as another consumer. It will be a valuable data source for our marketing and our business analysis. And this can be done by Kafka Connect, which can act as ETL between our customer data and our business data. But why we do this? Why transferring data to another location? The answer is clear. We wanted our data layer and all of its resources to be fully dedicated to our application layer. And we wanted them to focus only on serving the user's requests as quickly as possible. So if you need some data for insiders, like a report for the financial team, you're not allowed to run queries on data tier database and put stress on your main database. Otherwise, you will slow down the service requested by users. Here, an ETL tool comes in, and it helps us to extract, transfer, load data between one database platform to another database platform, which in this case is our data tier on one side and our data warehouse platform on the other side. As we are dealing here with big, very big actually, data sets such as historical events, data logs, huge statistical data, we need a big data solution to store and process these data. But building a big data solution usually needs quite a few components to be implemented and chained together. And unfortunately, it's way beyond this topic to go through each component and talking clearly about their functionalities. But in this case, I'll go for Hadoop, for HDFS and data partitioning parts, and I'll choose Spark for MapReduce and in-memory data processing, and finally Apache Hive for hosting the actual data. Now we have all the necessary data for business analysis in one place, and it can be used by our business intelligence tools like Microsoft Power BI or Apache Superset to create custom reports, dashboards, or data visualizations. This is what CEOs, CFOs, and marketing teams are looking for. To complement the solution, we need to add other communication services to form the omni-channel we need to have with our users, such as being able to send SMS, being able to push notifications to their mobile devices, and having a chat service, having chat with them. I think they are essential and enable us to effectively communicate with our members. And last but not least, we need a complete suite of in-house monitoring solution to optimize our services and keep them running and healthy. This was just an overview of how a sample web app like LinkedIn is designed in an on-premises environment, and how different components and microservices are working together to serve a purpose. We also saw how difficult it is to make such an environment scalable, highly available, and moreover keep it patched and updated. Now it's time to see how different the cloud environment is and how Amazon Cloud offering will change our world and help us to tackle our issues. To begin, let's take a look of how we can duplicate our LinkedIn app, this time on cloud infrastructure. The main advantage of a cloud service is that you do not have to invest a huge capital to buy and build the solution yourself and then pay extra upfront for redundant resources. In fact, you enroll in a cloud service for free, and then you only pay for the resources that you consume, and the cloud can take care of the rest of the stuff like scaling and resiliency. First thing we need is to create a routed IP network in the cloud for our resources. There's a container resource called VPC, or Virtual Private Cloud, which can be divided into a number of subnets, just like our on-premises routed network. But the difference is, each subnet can be in a different data center, which is called availability zone, or AZ in short. Availability zone are physically distinct data centers that are well connected to each other, and the way we distribute and duplicate our workloads among these AZs make them extremely available. Another notable key point is you shouldn't be worried about how to configure different routers so they can direct traffic between different availability zones. In fact, you can treat the whole VPC as a giant routed LAN with a single layer 3 switch and multiple subnets around it. Well, that's it. Okay, AWS Cloud will give you its own managed DNS, which is called Route 53. After we provision our subnets, we need to decide which subnets should be accessed from internet and which ones should remain private. Simply, we can add a default route to the public subnets, which points to internet gateway, which is simply our virtual edge router. For our private subnets, we will deploy a NAT instance, one for each subnets, and then change the default route in each subnet to point to its respective NAT instances. The NATs guarantee that only outgoing sessions are permitted, so our workloads are protected, and at the same time they can fetch their updates and security patches from the internet. The next thing you need is a load balancer and optionally a global accelerator to receive the user sessions and distribute them to the nearest healthy servers. Servers or VMs are called EC2 here, and you can provision them with a variety of OS images, even your own custom one. And then you will have the option to attach a local SSD or HDD disk to each VM, which is called EBS, or Elastic Block Storage. Now the best part is you can register an EC2 to an auto-scaling group to automatically scale up or down based on the server loads and based on the policy that you define. That means the AWS will add more server instances or may revoke them based on the actual traffic or processing needs. One more thing, there's a health monitoring mechanism in auto-scaling group also that can automatically detect anomaly in an instance OS or in its running services, and will shut down the faulty one and then spin up a new fresh instance for you. for the relational database in the data tier, you can go with AWS RDS, which is quite friendly to set up and operate. With just a few clicks, Amazon RDS provides you with 6 familiar database engines to choose from, including Amazon Aurora, PostgreSQL, MySQL, MariaDB, Oracle database, and even a Microsoft SQL Server. And if you want to make things even simpler and further reduce your headache to create, for example, a Linux virtual machine, installing Nginx, MySQL servers on it, and then updating and patching them, you may opt to a fully managed service called Elastic Beanstalk Service, which is a serverless app stack. That means you don't have to worry about creating a network, then do subnettings, and then create the instances. But you can simply upload your code, and Elastic Beanstalk automatically handles the deployment of the app on the cloud. And it will take care of everything from resource provisioning to load balancing and even health monitoring. You can focus on just building your code rather than spending time managing and configuring servers, databases, load balancers, firewalls, and networks for them. And you don't have to worry about patching or updating the environment also. It will do all the stuff for you. For the NoSQL data, AWS has several managed database offerings. For example, you can use DynamoDB for storing key value data, such as users' profile data, and then a graph optimized database called Neptune. We can use AWS Neptune for storing users' friendship network. And for the data cache layer, you can have Elastic Cache for all databases in data tier. It can act as a front-end in-memory cache layer for all the SQL and NoSQL backend instances. As a side note, I should mention, whenever you provision a multi-AZ DB instance, Amazon RDS automatically creates a primary DB instance and then a standby instance in a different availability zone and synchronously replicates these two. Plus, you can have multiple read-only replicas in each availability zone to improve the read performance. And whenever you need to connect your VPC to AWS managed services, you can use Amazon Private Link. By having a private link and private endpoint, you can access different AWS services without exposing your traffic to the internet. For content filtering, Amazon Rekognition makes it easy for you to add image and video analysis to your application's workflow using deep learning technology. You don't need to be a machine learning expert to use it. With Amazon Rekognition, you can simply identify different objects, people, facials, text, scenes, and detect types of activities in images and videos, like someone playing chess, for example. As well as you can detect any inappropriate content and activities, like someone doing, okay, forget about it. Let's move on. For media conversion, we can write a Lambda function. So as soon as a video is uploaded, it will invoke Elastic Transcoder. It converts media files from their original format into different formats, optimized for playing back on devices such as smartphones, tablets, or PCs. A Lambda function will generate a URL to get embedded in client-side running code. For persistent file storage, there would be a very cheap and durable managed storage, which is called S3, and it can be used for storing all your unstructured data. And this is not just about simple media sharing. These days, social medias are the best platforms for playing ads and targeting customers, and in return monetizing with playing video, just like YouTube. Amazon has a comprehensive media tool collection under the name of Amazon Elemental. it do all the stuff from creating and converting medias to contacting ADS or ads decision servers and insert or overlay the ads in videos or on top of a video. It can report back the whole statistics of how many times an ads was used by a user and bill the customers accordingly. For faster data delivery, we deploy CloudFront service in AWS Edge location close enough to users in every region, which will act as a cache or content delivery network solution and will cache static contents for users. Okay, let's move on to other blocks. Amazon offers both managed Kafka service and Kinesis. Kinesis is Amazon managed real-time data streaming service, and it's massively scalable and durable. Kinesis can continuously capture gigabytes of data per second from hundreds of thousands of sources, such as website click streams, database event streams, financial transactions, social media feeds, and other events. Captured data then will be transferred into the databases in the data tier to alter the user feed in real time. And it can be pulled back by big data for data analytic. So you can click a post and you're instantly served with more related posts as you scroll down the page, and you alter the business data sets at the same time, which indicates what is important to users. For all data sets we need for analytics that are out of the scope of Kinesis, we may use Amazon Glue, which is a fully managed ETL service, to load and transfer the desired data from our data tier and send them to our cloud big data platform, which in this case is another AWS managed service and is called EMR, or Elastic MapReduce. It can analyze and segment users, understand user preferences, and deliver more effective ads to them. And with the help of Amazon Athena, we can query and collect metadata from S3 buckets using a standard SQL, which then we can push them into our data warehouse. And the last step in this block is to publish all the process data in an AWS data warehouse solution, which in this case is Amazon Redshift. With Redshift, you can query petabyte of structured and semi-structured data across your data warehouse and your operational databases or your data lake just by using standard SQL query. And for the data visualization and bringing the data insights into our BI dashboard, we can use AWS QuickSight. Amazon has its own managed services for email, message queuing, and push notification service, as well as a complete set of tools for operational monitoring and automated event handling, which is called CloudWatch. And that's pretty much it. It's just like building a Lego set. The only thing is you just need to know how to prepare the cloud for your intended use, and then how to put your workloads on the cloud, and then connect these building blocks together. Here comes the coolest part. We can treat our cloud infrastructure design as a code. It is called IaaC, or infrastructure as a code. At first it seems a fancy word, but simply it means that we can collect and define all the cloud requirements in a YAML or JSON template files. And with the help of a service like Amazon CloudFormation or Terraform, we can launch or update the infrastructure by just committing our template files. Oh, and there is an even drag and drop designer tool in CloudFormation, which allows you to easily build or make changes to these templates. In AWS, we can use CodePipeline, which automates the build, test, and the deploy phases of our code release process. It runs every time a code changes and does all the required steps to the process of our code release just based on the workflow that we define. This enables us to rapidly and reliably deliver features and updates to our users. And for those who loves GitHub or any other kind of repositories, we can easily integrate AWS code pipeline with those third-party services. For smaller project though, we can use CodeStar, which can build the whole CI/CD pipeline in few minutes based on predefined templates. It's just a faster pipeline setup. Okay, this was a very top-level view of Amazon AWS Cloud Services. But one of the biggest misconceptions about cloud computing is that some might think that companies generally pick a single cloud provider and then stick to it for all their computing needs. In fact, it's quite opposite. Businesses use different providers for their different workloads. The good news is, despite all of cloud differences and uniquenesses, their design concept and their workflow in all of these cloud services are very the same, and you can easily switch from one to another. Well, in the last part of this presentation, I pictured commonly core services and resources from 3 major cloud providers and put them side by side so you can find the equivalent service for each of them. Take your time, pause the video whenever you need, and please get familiar with these terms because they will be a part of your technical language in near future. Thanks so much for being my learning partner, and I hope to see you in the next one.